Hello everyone, welcome to join us. Today's class will give you an outline of machine learning. We will talk about what is machine learning and introduce different types of learning, such as supervised and unsupervised learning. You will also learn how to evaluate the algorithm's performance. After today's class, you will be able to solve easy classification and regression problems using machine learning. What is machine learning? Machine learning arises from the question, can a computer learn to perform a task by itself? So machine learning is about how to make a machine learn from data automatically. Here are two figures shows the difference between classical programming and machine learning. About classical programming, the machine accepts rules and data and then generates answers based on the rules designed by the programmers. For example, a word editor accepts the input from keyboards and then print the articles on the screen. On the other hand, the machine learning algorithms accept data and answers as inputs and will generate the rules automatically. In other words, it learns the rules from the data by itself. This is the main difference between machine learning and the classical programming. By the way, in machine learning, we usually call the process of learning training. The machine learning flow can be roughly divided into three phases. The first one is data preprocessing. We need to collect a lot of data, usually have to label them and extract features. The second phase is to define a method to evaluate the performance of our system. We need to choose the right loss function and the matrix to get an accurate model. The third phase is the training phase, also called learning. It's to use an optimization algorithm to update the parameters of our model. In other words, we try to minimize the loss defined by our loss function. The lower the loss, the higher the accuracy of our model. There are three main types of machine learning. They are supervised learning, unsupervised learning, and reinforcement learning. Supervised learning can be further divided into classification and regression. Unsupervised learning can be further divided into clustering and dimensionality reduction. The main difference between supervised learning and unsupervised learning is that supervised learning has a teacher to label the data. In fact, teacher is just a nice way of saying workers. In practice, we usually have millions of training samples, which requires a lot of workers. On the other hand, unsupervised learning does not require workers to label data, although we also need to define the loss function to evaluate the performance. But in general, it can learn from the data characteristic automatically, so it's more close to the general intelligence. However, the performance of supervised learning is much better than unsupervised learning, so supervised learning is still the mainstream. Recently, there is a new type of machine learning called self-supervised learning, which can be viewed as an enhanced version of unsupervised learning and has achieved great results. We can further divide supervised learning and unsupervised learning into two categories based on the type of data. If your data are discrete data, then for supervised learning is a classification problem. If your data are discrete and you want to perform the unsupervised learning, then it's a clustering problem. If you have continuous data, then you want to perform supervised learning, then it's called regression. For unsupervised learning, this is dimensionality reduction. Almost all the algorithms are implemented in a Python library called scikit-learn. Here is the algorithm cheat sheet. It can help you to select the right algorithm for your problems. Let's take a look at this sheet. Start from here. The first question is to ask if you have more than 50 samples. If not, please go back and get more data. If yes, then check if you want to predict a category or not. If you want to predict a category, then your data are discrete data. The next question is if you have a label data or not. If yes, it's a supervised and discrete data, then it's a classification problem. For classification problem, you can choose the support vector machine classification or many others like k-nearest neighbor or naive Bayes. If you don't have label data, then you are doing unsupervised learning for discrete data. Then it's clustering. The first question of clustering is that do you know the number of categories of your data? If yes, then you can use the k-means clustering algorithms. K is the number of categories. But k-means is slow, so if you have a large data set, so you can use the mini batch k-means. If you don't know the number of categories, you can still use unsupervised learning, such as mean shift or Gaussian mixture models. On the other hand, if you want to predict a continuous data, it's also called predicting a quantity. Then if you want to predict the quantity of continuous data, it's regression. For regression, we have a different regression method. So we have a lasso, elastic net, or rigid regression. If we are not going to predict a quantity, then we are doing dimensionality reduction. The algorithms we can use are principal component analysis and other LLE or spectrum embedding. So this sheet can help us to choose the right algorithm for our problem. Here is the website of scikit-learn. It not only provides examples of using their algorithms, but also give an explanation about the theories behind those algorithms. So if you have any questions or want to understand how an algorithm works, you can visit its official website. Another way of classifying machine learning algorithms is based on their philosophy. This taxonomy was proposed by the Pedro Domingos. He proposed there are 5 types of machine learning. The first one is evolutionaries, which is based on the evolution theory proposed by Darwin, the survival of the fittest. The second one is connectionist. They believe that we need to build a model that based on how our brain works. In other words, they want to imitate how the neural networks works. So they are called connectionists. They care about the connections between neurons and the weights on each connection. The third is the symbolist. They view a model as a set of logical rules, and by dynamically combining all set of rules, we can answer all the questions. The fourth one is called Bayesian. Their models are based on the Bayes theory from probability. For example, they will calculate the probability of occurrence of different features and use those probability to build a model. The last one is analogizers. For new input, they will find the most similar pattern in the data set. find the most similar sample in the dataset, and then classify the input as the same category. The 5 types of machine learning algorithms have their own advantages and disadvantages. Each of them are good at some type of problems. Evolutionaries are the followers of Darwin's theory, survival of the fittest. So only the people that can fit the environment can survive. Right? The most famous algorithm of evolutionary is the genetic algorithms. Okay. Here is an evolutionary of human from monkey to upright human, and then today we are work like monkey and typing computers. So the most famous algorithm in evolutionary is genetic algorithm. The key point of genetic algorithm is crossover and mutation. Crossover, you can exchange gene of different people, right? Different human exchange gene. And then the mutation is that you can have some randomness in your gene. So today we still use genetic algorithm. We use it to search the neural network model. Let different types of model has crossover and mutation, and then compete the accuracy of each model. And the model with best accuracy will survive. The connectionists want to build models that are similar to our brain. So this type of algorithms are called neural networks or deep learning today. Here's a brief picture of our neurons, the biological neuron. So for a neuron, there are a lot of tree-like, a lot of branch input called dendrite, and this will have a very long connection to other neurons. It's called axon. So to build a model similar to our brain, we will have multiple layers of neurons. Each neurons calculate the weighted sum of the input and go through an activation function, then pass the output to next neuron. All right. So this is how connectionist, how neural networks work. Today, deep learning has achieved best results in almost all fields of machine learning. Deep learning has created a revolution in artificial intelligence. Symbolists focus on finding the rules. The popular algorithms of symbolists include decision tree, expert system, rule-based system. The rules found by the decision trees can be easily interpreted by humans. Therefore, it was a very popular type of machine learning before. However, it cannot be applied to complicated tasks like natural language processing or computer vision tasks. Here is the decision tree for prediction of survival rate of passengers on Titanic. So first, the decision tree. The first decision is ask if the passenger is male or not. If no, then you maybe survive. You have very high survival rate, okay, 36%. But if you are male, then check if you are old or young, or you are children. If you are children and if you have severity less than 2.5, then you still have a chance to survive. Otherwise, you will die. This small decision tree shows you how symbolists learn the rules of a prediction problem. The Bayesians build their model based on the Bayes theory, the conditional probability. Here's the formula of base theory. It says that under the observation of a feature X, what's the probability of this data belongs to class Y? And this formula used base theory can be right in this form. In this form, we just need to know the probability distribution of class Y, it's called prior, and the likelihood given a label class Y, what's the feature X, probability of feature X. And we need to assume the underlying probability distribution of our model. Bayesian algorithms such as naive Bayes is good for some problems such as email spam filter. The idea behind the analogizer is best described by this famous old saying, like father, like son. So for input, it belongs to the class of the training data that are most similar to it. Right. Here is an example of k nearest neighbor. KNN is the most easy analogizer's algorithm. Here's an example from Wikipedia. Suppose we have two classes. One is blue square, another one is red triangle. Now we have a new input, which is shown in green circle. Okay. We draw those data in the feature space, feature plane, and if the green circle is most similar to the samples nearby. Okay, so suppose we set k equals 3, or we use 3 nearby neighbors to design the class of the green circle, and we find that there are two red triangle close to the green circle and one blue square close to the green circle. So in this black circle, there are k. If we select k equals 3, then the 3 samples is in this range. There are two red triangle and one blue square. So the input belongs to the red triangle. So use KNN, we can just find the feature that nearest to the input and count. Use voting to find the majority class. But the class will change with the selection of k, right? If we select k equals 3, then in this case, the green circle will belong to the red triangle, right? Red triangle. However, if we extend the k to 5, in this case, the 5 nearest neighbors, there are 3 blue squares and only 2 triangles. So now if we set k equals 5, then the green circle will belong to blue square. KNN is simple and usually accurate. And one advantage is that you don't need to train a model because it just compare the input with the training data. Before we move on, let's review the types of data. Data type is also called the measurement scale in statistics. First, we can classify our data type into discrete and continuous. Discrete is also called categorical, and continuous is also called numerical. There are different names for the same thing. The categorical data can be further divided into nominal and ordinal, while the numerical data can be further divided into interval and ratio. Let's look at the first type of data, nominal data. Nominal data are labeling variables without any quantitative value. Okay. In other words, nominal data are used to represent classes or labels We usually encode nominal data by one-hot encoding in machine learning. Some examples of nominal data include gender. Gender usually have two classes, female or male. Or what languages do you speak? English, French, German, Spanish. So here are four classes. We use nominal data to represent different classes. So it's the most common type of data. The second one is ordinal data. Like nominal data, ordinal data are also discrete. Ordinal values represent discrete and ordered units. The difference is that the order in the data is now meaningful and important. An example of ordinal data is the educational background. We can use ordinal data to represent the educational background. For example, use 1 represents elementary, 2 represents high school, and 3 represents undergraduate, 4 represents graduate. Now the number not only represents the different class, but also the higher the number, the higher the educational background. The next two types of data, interval and ratio, are continuous data. Interval values represent ordered units that have same difference, but they don't have a true zero. Therefore, we seldom use interval data in machine learning. One example is the temperature. There are two types of measure for temperature, Celsius and Fahrenheit. Both Celsius and Fahrenheit can be used to measure temperature, but they don't have the same 0 point. The last one is ratio data. It's a continuous data, like interval data, but it has an absolute 0. So it's the most common continuous data type. It can be applied to both the descriptive and the inferential statistics. There are many examples. Here are one example to measure the weight and height. As we know, machine learning is based on statistics. Here's a comparison table of the terminologies used in machine learning and statistics. In machine learning, we call a model network or graphs. In statistics, they are models. But in fact, we also use models more often in machine learning. And the parameters of the model in statistics are called weights in machine learning. And the learning is called fitting in statistics. There's an important concept called generalization in machine learning, which means your model need to perform also well on the test set. In statistics, it's called the test set performance. The supervised learning in machine learning, there's no comparison terminology in statistics. So in statistics, it's just regression and classification. About unsupervised learning, there's also no corresponding name. It's a density estimation and clustering in statistics. The other two are not important terminology, just a sarcasm. That in machine learning, the price of the competition is usually around 1 million, while in statistics, the price is just around 50,000. And here are some places that's nice to have a meeting. We know all the conferences are now in virtual. Now let's look at some examples to get the insights of different types of learning. Let's start from the classification first. The most famous classification example is the iris flower classification. There are 3 types of flowers in the iris dataset. The first one is iris versicolor. The second one is iris setosa, and the third one is virginica. The flowers can be classified based on the length and width of the petal and the sepal. Our first job is to extract the features of the flowers. Features are the distinctive attributes of a thing. For iris flowers, the most distinctive attributes are the width and the length of the petal and the sepal of the flowers. So we can easily classify iris flower into 3 categories using just the petal and sepal. Therefore, we'll have 4 features by using the length and width of sepal and the petal. The 4 features are sepal length, sepal width, petal length, and the petal width. And we can summarize all the sample features into one table. In this table, each row represents one instance or samples or observations. They are the same thing. So each row represents one sample. The features are measured from a flower in the dataset. And the first 4 colors are the feature value, the length of sepal, width of sepal, and the length of petal, width of petal. The last column is the label of the class. We are doing supervised learning, so we need the labels of each sample. The label of the first sample is setosa here. The iris dataset have 150 samples, so we have 150 data rows in our table. The features are also called attributes, measurements, or dimensions. This is how we organize the training samples. There are other ways. For example, in practice, we usually separate the feature data and the class labels into 2 different files. Let's visualize our dataset using the features. Because we cannot visualize 4-dimension features, we select just 2 features from here. We select the length of sepal and the length of petal, and draw the example based on the length. We can see from this figure that 2 classes, versicolor and virginica, are close to each other. Another class, setosa, are far from the other 2 classes. For the setosa and the other classes, because they are far away, we can easily find a line that separates setosa with other 2 classes. So it's called linearly separable. However, for versicolor and the virginica, they are not. We cannot find a linear line that easily separates those 2 classes. We may need a curve to separate those classes. Then it's called linearly unseparable. So iris, versicolor, and the virginica are not linearly separable. We need to find a nonlinear line to separate those 2 classes. Let's build a binary linear classifier to classify setosa between versicolor and the virginica. Because versicolor and the virginica are not linearly separable, so we view those 2 as one class to simplify our problem. So our goal is to find a linear equation, to find a line that can separate setosa with the other 2 classes. So first, we make the petal length input as feature x1 and the sepal length as feature x2. Please note that in this figure, the x-axis represents feature 1 and the vertical axis represents x2. In geometry, usually we use x and y to represent the horizontal axis and the vertical axis, but here both axes are features, so the horizontal axis is x1 and the horizontal and the vertical axis represents x2. So for this equation, we can write a linear equation that w1 x1 plus w2 x2 plus the bias equals 0. So we can use this formula to represent our linear equation. Okay, and we can rewrite the linear equation using the matrix multiplication. So we can write the weight as a row vector and the feature x as column vector. So we can rewrite our formula using the linear algebra. This is important because we have more than two features, so we want to be able to represent our data as vectors. So when there are more features, then we can just use the feature vector. So this can be further write as a weight vector. The transpose of the weight vector multiplied by the feature vector x. So we use w to represent the weight vector and the x represent the feature vector. Usually we use bold font to represent vector. Okay, so this is our classifiers. How can we use it? To use the model, we just put the calculate x input using the trend weights, and we get a new output y prime. So y prime is our prediction. Okay. If y prime, if we use the feature from Setosa, suppose we use the feature from Setosa and use the pre-trained weight to and the bias. B is called bias in our in the formula, and then we will get the output. We want the output. We want the prediction y prime less than or equal to 0. Depends on if you want equal. So we want, because the Setosa is at the lower left corner, right? It's at the lower left corner. So when we want our classifier, when we get input from Setosa, we want our classifier outputs minus value less or equal to less than 0. Okay. Now if we have input from versicolor, got input from versicolor feature input, then we use the pre-trained weight of our model. This time we will want our output larger than 0 because they are at the upper right side, at the right side. So this is how we use the linear classifier to classify two classes. It's a binary classifier. Now we have a simple linear classifier. Let's train our classifier. First, we need to define the loss function. L. The loss function we can use a simple square loss to calculate the difference between the true label y and our prediction x prime, y prime. Okay. And then we can calculate the gradient. The gradient of the loss function will be, ignore the constant, will be just the difference between true label Just the difference between the true label y and y prime. We can use delta to represent the difference. So how can we update our weight? Our new weight, make it WD plus 1, will be the original weight plus the gradient multiplied by x, right? So we can use the gradient and the input x to update our weight. But note that we usually add a factor, we call it learning rate. We call it learning rate alpha. Because if we just add the gradient multiplied by x, that will be a very large value, and our training will be unstable. If there's a large if there's an outlier in our dataset, it will cause our training very unstable. So how can we update all the weights? We then use a loop to continuously keep updating our weights until the error converges. Until the error delta approaches 0 or to a value that acceptable. This algorithm is called perceptron, which was proposed by Frank Rosenbaum. The perceptron algorithm is simple and effective. However, it can has unlimited number of solutions, and we don't know which one is optimal. The support vector machine, SVM, try to answer this question by making an assumption. SVM assumes that the optimal classifier, the red line here, is the one that has largest margin between both classes. To calculate the distance between the classifier and the sample points, we can draw two hyperplanes. So the dashed line are the hyperplanes. There are two hyperplanes. One is for the blue classes, and the other one is for the green classes. In SVM, we define the idea of blue class as 1, and the idea of green circles -1. So by defining the hyperplane, we can calculate the distance, the margin between those two hyperplanes as 1 divided by the norm of W. So if we want to maximize the margin between those two hyperplanes, we just need to minimize the norm of W, norm of the weight of our model. So this is SVM. Compared with perceptron has many different classifiers between those two hyperplanes, right? And perceptron doesn't know which one is the optimal classifier. And SV1 try to answer this question by specifically assign that the best classifier is the one with largest margin. So our goal is to choose the hyperplanes that have the largest separation margin, and that is to minimize the norm of the weights of our model. Let's design the loss function of SVM. First, we want all the blue circles larger than this hyperplane, and all the green circles less than the second hyperplane. So first we design the label of all the blue circles as 1. So yi equals 1, and all the labels for the green circles are -1. So in SVM, the labels of the two classes are 1 and -1. Then let's use the hyperplane to classify the blue points. Suppose the feature of this vector is xi, then our equation will be weight multiplied by the feature x, right? Minus bias should be larger or equal to 1. So our first prediction of the blue circles, we hope the output prediction y prime I will be larger or equal to 1, right? And for the green circles, the equation will be our weight w multiplied by the green features, okay, and minus the bias will be less than 1, or less than minus 1. So for the green circles, we want our prediction. We want the features of all the green circles when classified by the hyperplane will be less than minus 1. Okay. Then we can combine those two terms together. We can combine those two terms together by multiply the prediction y prime with the true label. With the true label yi, then this term should be larger or equal to 1. Should be larger or equal to 1. Okay, so this is our prediction. We want the two hyperplanes can classify all the points, all the data. Now let's define the loss function. Suppose the loss, function, First, we want to see if we misclassify a point. Suppose we have a point here, or we have a blue circle here, right? Then we want to calculate the difference, the distance between the blue point and the blue hyperplane. Okay, so we can use the distance between the blue point and hyperplane as the penalty. So our loss will be 1 minus y label multiplied by our y prime prediction. Okay, that will be our loss. But what if we correctly classify points? Suppose what's the penalty of the points? If the circles are correctly classified, there's no penalty. But if we use this loss function, right, it will have a large minus value. The far away from the hyperplane, the larger the minus value. However, we don't want the minus value. We don't care about the correct classified circles, so we will use 0 whenever your loss function is less than 0. Then it means we have done the classification correctly. So we will use a max function. The max function is used to ignore all the correct classification, right? So this is called hinge loss because whenever we classify the points correctly, we ignore the loss. So this is the spirit of loss function. Loss function only penalize misclassified data. Now let's write SVN as an optimization function. Okay. So first we need to have an objective. Our objective is to minimize the distance, maximize the distance by minimize our weight, the weight of our model. But here we will use the square. This is because we will do the gradient descent, right? So we write our optimization function as this. Okay, by minimize the norm of the weight, the weight of our model, we can maximize the distance. Okay, then we will subject to all the hinge loads of our samples, right? So we will write I to n. We need to calculate the hinge loads of all the samples, all the data in our training samples, right? Okay, and we can calculate the average of the whole. Then we can combine. We can combine those two terms. And calculate the gradient. We name this function j of w. So we can add the objective function with the constraint, with our constraint, just multiplied by a cost parameters. C is the hyperparameters, which can decide how important the loss, the misclassified loss, right? If we have a very large C, then it means our algorithm need to focus on correctly classify all the points. Okay, so this is the our objective, our final objective. So now we can calculate the gradient, right, of our j of w against the w. And finally, the results will be the result will depend on your classification is correct or not. If you successfully classify the point, then the loss will be zero. The loss will be zero. Otherwise, it will be derivative of your hinge loss. So eventually, let's omit some of the details, but eventually it will be looks like this. It will be W if you correctly classify the point, which means the hinge loss is zero. Here we can omit the bias by writing the bias, combine the bias into the new weight. Remember, we can write the weight as a vector, so add one additional column can combine the bias with the weight, so that we just write wx. And also we usually omit the transpose, but if you omit transpose, you need to add a dot. dot product. Okay, so if your hinge loss is 0, which means you have correctly classified this data, this circle, so then the gradient will be W. Otherwise, it will be W minus, okay, the hyperparameter multiplied by the yi and the xi. Otherwise, okay, so we have written SVN as an optimization problem and calculate the gradient. SVM tells us how to select the optimal classifiers, which is pretty good. However, there's still a problem that SVM is still a linear classifier, so we don't know how to separate nonlinear data. Okay, remember in our iris flower dataset that versicolor and the Virginia are not linearly separable. We need to find a way to separate nonlinear data. To separate the data not linearly separable. Here's the answer of SVM for the nonlinear classification. It's called kernel trick. The assumption is that suppose we have a nonlinear, we need a nonlinear classifier in a 2-dimension. But we cannot do this because SVM is linear. So we can try to project the data into higher dimension. For example, we can project the 2D data into a 3D dimension. And maybe in the 3D dimension, we can find a hyperplane that can is linear and it can separate those two data. Okay. So we want to project data into higher dimension. But we can just calculate the distance between the data and this is called kernel. We just need to know the distance relationship between those data points. Then we can assume that we have project data into higher dimension. Then we can try to find a plane that can separate the data that are not linearly separable in our original vector space. There are some examples from the scikit-learn. The first is linear kernel, which means it's still a linear classifier. So we can find that the boundary or the classifier are all linear. The second one is also a linear kernel. But for the third classification, the author used RBF kernel for classification. So we assume that there's a hyperplane that can separate those data in a higher dimension. So when project back to our 2-dimension plane, then we can see a curve, the curve of the boundaries, right? So it's indeed can do some nonlinear classification. If we choose different kernel, it will have different effects. So this is how SVN deal with nonlinear classification. However, it's very difficult. It's time consuming to calculate the kernel, and then you need to search the hyperparameters. So now we find a better way to use the neural network to do the nonlinear separation. Another problem of SVN is that it's designed for binary classification. So we can only classify 2 classes so far. So how can we extend SVN to multi-class classification? There are 2 techniques. The first one is called 1 against 1, and the second is called 1 against all. So what is 1 against 1? What it means that we want to learn classifiers for each pair of the class. Okay. So for example, if we suppose we have 3 class A, B, and C, then for the 1 against 1, we need to learn 3 SVN classifiers. So first we learn the AB classifier, and then the AC classifier, and then the BC classifier. So how many classifiers do we need for n class? This is a question. Okay. The answer is that we will need the unchoose two number of classifiers for n class, right? So if we have 10 classes, then we will need to learn that 45 classifiers. So that's a lot of classifiers. The second approach is 1 against O. 1 against O is to first, suppose we select class A, then we combine the rest of the class. The rest of the class is the B and the C together as the negative example. Or suppose we make A the positive, then we can combine all the other classes as the other class. So there's only two classes. Then we need to learn a classifier that is classify A against BC. Then we choose class B and then learn a classifier to classify A and C. We combine A and C together. And for C again, we combine A and B and then learn a binary classifier to classify the C and the A plus B class. Okay, in this example, we learn 3 classes. For 1 against O, you only need to learn n classifiers. However, in this example, the unchoose 2 is also equal to 3. So those two techniques has the same number of classifiers. However, when you have a large number of classes, then 1 against O will have much less classifiers than 1 against 1. When there's an input, you apply all the classifiers and use voting to find the class that with most output. Find the majority class, and then it is your prediction. We can also use neural network to classify iris flowers. Neural network can easily learn nonlinear classifiers, so it can solve our problem. And here's an example from TensorFlow tutorials. So Google has made an example to use TensorFlow to classify iris flowers. And in their tutorial, they use a small network with 2 hidden layers and 1 output layer. So it's a 3 layer. The input layer, they use 4 features. To count the layers of a model, we don't count the input layer. So the network, the model has 2 hidden layers and 1 output layer. The output layer is softmax. We know the output dimension should be equals the number of class, which is 3 in the iris flower data set. So the output will calculate based on the input the probability of each type of iris, setosa, versicolor, and virginica. You can click the link to get the source code. Before we continue, let's look at feature engineering and feature learning. So we remember that the first step of machine learning is data preprocessing. We need to first collect data and handle missing value and do vectorization, also normalization. After doing all the preprocessing, we need to extract features. So feature selection feature design is very important. Good features still make learning easier. Although right now, machine learning do the feature engineering job for us. But we need to understand why good features make learning easier. Here's an example. Suppose we want to classify, we want to recognize the time on an analog clock. And the analog clock has 2 hands, short hand and long hand. A naive engineer a naive feature is we can use the position of the long hand and the short hand. So we can use the x1, y1 to represent short hand and the x2, y2 to represent the position of long hand. Then we will have 4 features. However, we know that they are moving in circles, so we can use just the radius, right? Theta. We can just use the angle of the hands. Then if we just use the angle, then we will have only 2 features. So compared with the hand locations, we are now have only 2. Originally we have 4. So we reduce the dimension of the feature space by half. So if we select our feature selection is very easy because the lower the dimension, okay, the easier the model to train. So features engineering is important to still important for learning a good model. Let's look at another classifier based on the Bayes theory. So there's a classifier called naive Bayes. Remember the Bayes theory is based on conditional probability, right? So we can write our model as based as the conditional probability. For example, the input x are the features of the image, or other features in the iris flower set, the length and width of sepal and the petal. Okay, then based on the features, what's the probability of the input sample belongs to class Y? So we can write the model as a conditional probability. Based on the features we have seen, what's the probability of it belongs to class Y, right? And then we can use Bayes theory to write to train the model. Okay, so using Bayes theory, the first we have a prior P of Y. This is the distribution of the class in the training sample, and then the training data based on the known samples. We have labels. So based on a certain class, what's the features, right? What's the features of the class? So it's called the likelihood. The evidence are the same for all the classes. So sometimes we omit it. Okay. So here's the Bayes theory. So what is naive Bayes? So what's the naive means? The naive means that Bayes assumes that all the features are conditional independent. So by making this assumption, we can convert this likelihood function into multiplications of individual conditional probability of individual features. This will make calculation much easier, right? Bayes theory. Okay, so the naive assumption makes calculation very easy. You just need to calculate the conditional probability of each feature and then multiply them together. However, this assumption is usually too strong, too naive, so the performance may not good for complicated jobs. Okay, so as I said, because the P of Y evidence is the same for all the samples, so it can be omitted to just calculate the conditional probability of the features and multiply by the prior. Then you can train the model. You can train your model. You can train your model by maximize the probability for each class. Also, to use naive Bayes, we need to assume the underlying probability distribution. The go-to distribution is Gaussian distribution, right? Okay. Fortunately, we don't need to care about the details in scikit-learn, right? So here's a scikit-learn example. We can just import the Gaussian naive Bayes model from the naive Bayes in scikit-learn library, and then we knew a model. It's called GNB. Then we call the fit. We can download the iris dataset from scikit-learn datasets, and then we fit the data with its labels. It's called target in the scikit-learn datasets. Here, then we can directly predict the data. This is the performance on the training dataset. Then we can print the results. Okay, so this shows how easily we can use a model by using scikit-learn. Okay, how easily you can use a model in scikit-learn. We just import a model and then fit it. Then we can use it to predict. Of course, there are some more hyperparameters that we can tune, but we can first use a default setting. Okay, so I write a notebook to evaluate all the classifiers that mentioned in previous examples on the iris flower dataset. Here's the notebook link. So first we import a metric accuracy, and then we import the linear models, all the linear models, SVN, KNN, and also the dataset Gaussian naive Bayes. Okay. Then we load the iris dataset. There are 150 training samples in iris dataset. Okay. Here we make all the classifiers in a dictionary. We make a classifier dictionary. So the key is the name of the classifier, and the value is a model. So all the machine learning models in scikit-learn, they have a fit function, right? They inherit from the same parent class. So there's a parameter we use KNN. K equals 5. We select 5 for our KNN. And there's a cost function for SVN. Okay, so we can use the dictionary, and then we can use the for loop to train our model, right? So for the name and the classifier in the classifier dictionary, we can use items to get the key value pair, and then we can use the value, which is a machine learning model, to train, called a fit function. Because all the models in the dictionary has a fit function, so we just call a fit function, right? And once we get fit, we can print the name of the model and the accuracy. So by making all the classifiers as a dictionary, we can use a simple for loop to train all the models, and then see the results. Okay, so here is the results of prediction on iris dataset. The original iris dataset does not have a test set. So fortunately, the Google TensorFlow example, they provide a test set. So I use the test set from Google to evaluate all the algorithms. Okay, here's the link of my notebook. So as we can see, the first two are k nearest neighbor at 5. So the simple KNN achieved 96.67%, but the weighted KN has better performance. It achieved 100% accuracy. Because the test sample, the test data set is very small, so most algorithms achieve the same results, but we can still see some difference of the algorithms. The third one is the perceptron. We can see that perceptron performs worse than other algorithms. Another algorithm is called L1 logistic regression. We leave this model in the regression section. We will introduce it later, but here we list it to compare with others. Okay, the linear SVC is the support vector machine, support vector classifier. It's achieved 100% accuracy. You may wonder that I said the dataset has some the versicolor and the virginica are not linearly separable. So how come the linear SVN achieved 100%? Well, it depends on your dataset, right? So in this data set, it's happened that all the test samples can be classified by the linear SVN. So linear SVN achieve 100% accuracy. This tells us that your performance is actually relies on your test data set. So if your test data set is too small, it's not very representative of your model. It's not distinguished. You cannot find a real difference of the model, but we still can have an overview of all the methods. So generally, KNN and SVN are good methods. Next is the naive Bayes. So naive Bayes has achieved similar results with others. The last one is the 3-layer DNN. I report the accuracy in the Google tutorial, but you can implement it using Keras. Anyway, in this small data set, KNN didn't perform better than others. However, when you will see the power, of DNN when on the large scale data set, or when the data are numerous. You can download my notebook and try the algorithms by yourself. Now let's look at regression in supervised learning. Regression is used for continuous data, such as house price and the stock price. The linear regression wants to find a linear model. We can write a linear model y prime equals w dot x plus bias. So we want to find a linear model that has minimized the total square loss. Here's a picture. So in other words, we want to find line of best fit. So suppose the black line is our linear model. We want to find the line of best fit that minimizes the total error, square of the errors. The errors are in red line. So our predictions, whenever there is an input x, the horizontal axis is input. Whenever there's an input x, our prediction is on the line, right, on the black line. And the difference, the distance between the true sample, the blue circle, and the dot on the projection on the black line, the distance are the errors. And then we want to minimize the total square errors of all the samples. So our goal is to minimize. Our goal is to minimize the errors. The errors is all the samples, right? The error between the true label yi and our prediction y prime. The square of the difference between the true label and the predictions. So we want to minimize the total square of the errors. It's called the least squares. Okay. And actually, we can solve this equation directly. Let's just reformulate our equation by writing x before w, because the dot product is a scalar, so we can change the order of our weight and the input x plus the bias. So actually we can write the bias and weight as one column vector. So by rewrite our formula as vector multiplication, we can incorporate the bias into the weight. So weight is one of the byte. So then finally it will be equal to new x or new x dot w. We can call the input x with bias with one entry or x hat or x hat. Then we can solve the w. We can solve the weight directly using the pseudo-random formulation, right? Remember the pseudo-random. So we both multiply both sides with x transpose to make x a square, and then we multiply both sides with the inverse matrix of the x transpose multiplied by x. It's actually x hat. Then we can solve the linear equation directly. So the linear regression model is the first model for regression problem. And if we have an inverse matrix of the x transpose multiplied by x, we can solve this equation directly and find the parameters of our weights. Here is the pseudo inverse solution for our least squares problem. So we can use the pseudo inverse to calculate the weights of our model directly. And the equation has a unique solution if and only if, first, the columns of x are linearly independent, and the x transpose multiplied by x is invertible. So if our model satisfies those two questions, then our model has a unique solution. Let's apply regression to a real data set. Here is the data set in scikit-learn. It's a diabetes data set. There are 10 features. The age, body mass index, average blood pressure, and 6 blood surround measurements. And there are 442 diabetes patients. All the features are normalized to have mean 0 and the square length equals 1. Okay, so here's the brief profile of the diabetes data set. Okay, but in our case, we use only one feature to predict diabetes possibility. Our target is between 225 and 346. Okay, here's our target, and we use only one feature because we want to visualize it. Okay, so the vertical axis is the diabetes index or something as the target, and the horizontal axis is the BMI. From this figure, we can see that BMI may be a good feature for predicting diabetes. Here is the sample code of drawing the regression line. Okay, so first we import the matrix mean squared error from the scikit-learn library. Also, we import linear models and data sets. Then we load the diabetes dataset using the datasets of scikit-learn. And then we select only one feature, the BMI. We select the BMI features. And then we split the data into train and test set. Okay. After that, we just call the linear regression in a linear model to build a regressor and fit the training data with the train label. Okay, then we can make predictions on the test data set. Finally, we can use the scatter plot to draw all the samples on the plane, on the tests and the labels on the plane, and then plot the line, plot the prediction line or the regression line. Okay, and show the results. The results is here. So we can use scikit-learn to draw the regression line and make predictions or train our regression model. We have learned a linear regression model. From the scikit-learn cheat sheet, we can see the linear regression is here, stochastic gradient descent regressor. But there are still other regression algorithms, including lasso, elastic net, and the rigid regression. What's the difference between those algorithms and the linear regression? Let's move on to the next page to see the details. Now I want to introduce an important concept called regularization. Okay. Regularization can help you to avoid overfitting and have higher accuracy on test set. So first, we know that linear regression has two problems. First, it's sensitive to outliers. Outliers are data points, data samples that far from the mean. So if you have outliers, their large different value will affect your accuracy on test set. And also, machine learning is easy to overfit training data, especially when you have less data. You have small samples, small training data. So here's an example. In this figure, the red points are training data. Red points are training data. And the green points are test data. So suppose we only have two training data. This is a small sample. Then our model will be the red line, our linear regressor, right? Our model. It's perfectly fit the training data. It's perfectly fit the training data. However, when you apply the model to the green lines, you will see a lot of errors because the distribution of the training data are not similar to the test data. So one solution is to use regularization. Regularization will add some bias into the bias during the training. In other words, regularization will add some constraints to limit the weights of the training data and make training more difficult. But by making training a little bit more difficult, it can reduce the variance of test data. It can generate a new model. The blue lines. This is model with regularization. Model with regularization. It will add some constraint to make your learning more difficult. So you have some you reduce the bias. Okay, you add the bias. You add the bias of your new model. So for the new model, actually your error on the training set is larger, right? You can see that the error. Sorry. The error on the training set is larger than before. The red model has perfect zero error, perfect fit the training data. The blue line has some bias, right? Has some bias. The blue line has some bias, so it's shift from the perfect training model, but it will fit better on the test set. So regularization adds a small amount of bias during training to reduce the variance on test set. In other words, it's generalized better on the test set. You can see a perfect video from the StackQuest. In fact, the different types of regression, lasso and rigid or elastic net, Adjust linear regression with different regularization terms. Here is an example. Here's the cost function of linear regression. Here we use beta. In this figure is from this block. In this figure, the author used beta to represent weights in our model. So it's the true label minus the linear prediction of all features. So to visualize the regularization, we select two weights of our model, beta 1 and beta 2. So in those contours, on each contour, the costs are the same. Means that they have the same minima cost. But if we have same minima cost, we will prefer the weights that meet the constraint. So those constraints are regularization terms. By ending the sum of the L1 norm of the weights, then we call it lasso regression. So from here you can see that regularization is just the end constraint in our learning objective functions, and we can end a different constraint. From previous example, we know those constraints will make training more difficult. We'll add bias on the training model, which means you will have lower accuracy on your training model. However, you might have better accuracy on test set. Okay, so lasso will be equal. The L1 norm will be equal, visualized on the weight plane will be looks like a diamond, and our model will try to select the contour that intersect with the lasso region. Usually, intersection will be on the axis. Lasso will prefer to make some weights zero. Will prefer to make some weights zero because of the shape. Another method is called rigid regression. Use the L2 norm or square of L2 norm, and it will be a circle. The constraint area will be a circle. So the contour will maybe intersect at this point. This point will prefer some small values from both weights. So from those two examples, you can see how the regularization term prefer smaller weights to constrain the size of the parameters. And by constrain the size of the parameters, we can add some bias in our model and make our model more robust, can resist overfitting, and have better generalization on the test set. Google also provides an interactive code example for regularization. You can open a notebook here. You can set the number of training epochs. Suppose we set it to 500. And here's the results that the model learns, the weights for each feature. There are 8 features. If you don't use any regularization, it will look like this. And then if you use L1 as regularization term, then you can see 3 of the 8 features are 0, which means we select only 5 out of the 8 features. Right? We remove 3 features. So L1 can be used for feature selection. And then if we use L2 norm, then the model will still prefer some small values for those 3 unimportant features. Right? L2 will prefer weights for all the features, and you can see by ending L2, the feature weights are smaller than no regularization. Here are the unit norms of different regularization terms in 2D vectors. They are what the different norms looks like in the 2-dimensional space. The first one is L1 norm. We have seen this. So it looks like a diamond. The second is the L2 norm. It will be a circle, the unit norm of L2 norms. And the third one is infinity norm. Then infinity norm will looks like a square in a two-dimensional space. Now we know that the three different types of regression algorithms, rigid, lasso, and the elastic net, are just a linear regression with different types of regularization terms. So for rigid regression, it's just a linear regression plus L2 norm regularization. Alpha is just a hyperparameters to choose the importance of the regularization term. Some people use lambda. Okay. Note that in rigid regression, we use the square of the L2 norm. Remember that the L2 norm is just the root of square sums of the features in the vector. Okay, but calculating the root is high computational cost. It has high computational cost, so we usually use the square of the L2 norm. For lasso, is the linear regression plus L1 norm, and for elastic net, it's use both for the L1 and the square of the L2 norm. Let's see how different regressor works on a real dataset. Let's use the algorithms to predict the house price in Boston. There's a dataset called the Boston House Price Dataset in scikit-learn. The goal or the objective is to predict the median price of homes in Boston area. This is a small dataset with 506 samples and 13 features. Here are the list of the features. The first is the crime rate by town, and the second is the proportion of the residential area. This is the over the 25,000 square feet, and the proportion of non-retail business, the industrial room per town. Also, there's a feature that if the house is close to Charles River or not. And also the nitrogen oxide concentration. And the average number of rooms per house. Also the age of the house is also important. This is the age proportion of owner-occupied units built prior to 1940. So it's a very old data set. And also there's a weighted mean of distance to 5 Boston employment centers. And also the index of accessibility to radial highways also, if the house is close to the highway or not, and the tax. Also the pupil-teacher ratio. So teacher is also important for the price of house. First of all, we need to normalize our data. We want to make all the features center around 0 and have a unit standard deviation. By normalized data, we can avoid that the feature with larger values will have larger impact on our model. So we need to make all the features center around 0 and have unit standard deviation. Also note that the quantities used for normalization, or the mean, the standard deviation of each feature, should be calculated using the training data. We should use the training mean and the standard deviation to normalize the test set. So here we can see an example. X is 0 means we calculate the mean for each feature. So this mean is also a vector. Okay, then we minus all the features in the training dataset with the mean and then divide by the standard deviation of each feature. And we then use the training mean and the training standard deviation for test data to normalize test data. We cannot use the mean and the standard deviation of test data. Okay, remember that the test data should be unknown during training, so we should not use even the mean and the standard deviation of the test data. I create a notebook to compare the different regressors on the Boston House dataset. Here is the notebook link. So let's see the code. First, we import the metric and the linear model from scikit-learn and the datasets. And then we load the Boston datasets and get the data and the labels. We can calculate the mean of the labels. So the average price we are supposed to predict is around 22. I guess the unit is $1,000. So it's a very old dataset, so the house was cheap. Then we normalize the data by make the features around 0 and divide by standard deviation. Okay, and then we compare 4 regressors. The first is the linear regression. The second one is rigid regression with hyperparameters 0.5 for hyperparameters lambda. And then the lasso we use 0.1 and the elastic net is 0.1. We didn't try to optimize the hyperparameters, so this results just for reference. You can try to optimize the hyperparameters by using cross validation. Okay, so let's do the training. Training just call the fit of each regressor, and then we predict to see the results on the training data set. Here's the comparison results of different regressors. We use the mean absolute error as our metric, MAE. And here are the results on the training data. We can see that rigid regression in this dataset has similar performance with the linear regression. The lasso and the elastic has slightly better results. Of course, we care more about the test data. There are 102 samples in the test dataset. And the same are the rigid regression and the linear regression. In fact, they have a slightly better performance on test data. But those two algorithms has same performance again. And then the lasso and the elastic net now has still better than the rigid regression, the linear regression. Okay, so here's the simple comparison results. Of course, we can still try to optimize the results by using cross validation to optimize the hyperparameters. We randomly select 0.5 for rigid regression. But from this simple example, you can still see that regularization help. Even on the training dataset, you can see the effectiveness of regression because it can help to reduce the effects of some outliers, and also still perform better on test dataset. Remember that we have learned how to use Keras to predict house price before. So here was the results. We use a 3-layer DNN to predict the house price. You can open this notebook to review the code. We have 2 hidden layers with 64 dimensions, and the final output layer is a single output neuron without any activation function. The total number of parameters is 5,121. The final comparison results are here. I add the result from the Keras notebook, which was 2.73 mean absolute error. Remember, our mean is around 22, so it's around 10% error. So from this example, we can see that our simple neural network model can outperform other traditional regression methods, including linear regression, rigid regression, lasso, and the elastic net. Now let's talk about a very important algorithm called the logistic regression. It's called regression, but it can also be used for classification. We'll see how later. Also, logistic regression plays an important role in neural networks. So what is logistic regression? It's actually, again, a linear regression model with an sigmoid activation function. So it's actually a linear model with an activation function, which is one type of neuron, right, in neural network. So we first need to understand what is sigmoid activation function or sigmoid function. Here's the formula of sigmoid function. It's 1 divided by 1 plus e to the power of minus x. X is the linear model. Okay, so this is sigmoid function. The output curve of sigmoid function is like prolonged S. It's an S-shaped curve. S-shaped curve. So it can be used as the output of a neuron. It can be used like the output of a probability because the output is limited between 0 and 1. So you can use this output of a probability. Okay. So why we love sigmoid function? This is because the derivative of sigmoid function is just itself multiplied by 1 minus itself. So the derivative of sigmoid is sigmoid multiplied by 1 minus the sigmoid function. So this is a very elegant result. We'll use sigmoid function very often. The output of the logistic function is still continuous. How can we use it for the binary classification? So how can we apply it to the discrete variables? The answer is that we need to find a decision boundary T. So if the output of logistic function is less than the threshold T, then it belongs to class 0. If the output of the logistic function is larger or equals to T, then the output belongs to class 1. So use the decision boundary T, we can convert the logistic output as binary classification. So here's the final formulation of logistic regression. We put the linear model into the logistic function. Here's our linear model, the linear model with weight W and bias B. Then we put this term in the logistic function, in the sigmoid function. Then this is our logistic regression model. Here we use the symbol P theta of x to represent that we want to we have a model with training parameters theta. The theta actually are the weights and bias, which we want to learn during the training process. The next step is to design the loss function for logistic regression. The loss function for logistic regression is called cross entropy loss. So first, let's define what's the cross entropy. Entropy is an important concept in many science fields, including physics or information theory. In information theory, it says that your information is inversely proportional to the probability that you have shown. Right? So it's inverse proportional to the occurrence probability of an event. This called information. In other words, an event is more important, more informative if it happens less, right? So rare event. So it's 1 divided by the probability of the event occurrence, and then this is equal to the minus, right, log 2 of p of x. This is called information in the information theory. And the entropy is actually the probability plus multiplied by the information. It's called entropy. So we can use the information to calculate the loss, right? So here are two loss functions. Suppose for the class y equals 0, for the class 0, the loss is that if your prediction is 0, then it's a correct prediction. Then this term is 0, then the loss is log 1. Log 1 equals 0, so there's no loss function. Otherwise, you will be penalized here. You will be penalized if your output prediction is closer to 1. If your prediction is far from 0, here's a correct prediction. If your prediction is far from 0, you will get larger loss. Right, so this is the loss term for class 0. On the other hand, if the correct label is 1 and your prediction is 1, then the loss is 0. Otherwise, you will be penalized if your prediction is closer to 0. Yeah. Yes, so this is the cross entropy. So for the binary classification, it penalizes for error prediction. Your penalty will grow exponentially if your answer is far from the correct one. Now we need to combine those two terms together as one loss function. If the label is 1, then we just multiply by the label with its loss term. So if the true label is 0, then this term will be ignored, right? So on the other hand, for the label 0, we use the 1 minus y, 1 minus the label is the term, and then multiply by the loss terms. So if the true label is y, then this term y minus y will be 0, and this term will be ignored. This term will be ignored. Then we can finally calculate the derivative of the loss function. And this long loss function actually has a very pretty derivative results, right? The term is very elegant. So it's actually just the true label y minus your prediction, y minus y prime multiplied by x. So the derivative is actually very simple. That's why we love cross entropy loss. Let's compare logistic regression with other classifiers on the iris dataset. Here is the result of L1 logistic regression. We actually add a regularization term, L1 term in the logistic regression classifier. And the result is similar to other methods. So naive Bayes and similar to 3-layer DNN. So logistic regression is also a good baseline model whenever you want to compare with your deep learning models. You can also choose logistic regression. Let's look at the most important concept in machine learning: overfitting and underfitting. Overfitting means that your model fits the training data so well that you achieve almost perfect results on your training data set. The breakdowns are the training data set. However, the true model should be the black line, right? The black line. So although you will achieve a perfect result on your training data set, you will achieve worse result on a test set than a simple linear model, because your model maybe is too complicated, has too large complexity, and your model can overfit the training data set. However, when you apply your model to the test set, you will get worse results. So don't be happy too early whenever you get a high accuracy on your training data set. Usually high accuracy is due to overfitting. On the other hand, underfitting means that your model is too simple. I mean, the dataset is your model, and the true model should be maybe a curve, more complicated. But your model is too simple that you underfit the training data, so you get worse result on both training data set and the test data set. Because deep learning model can have as many parameters as you like, so it's very easy to overfit, especially on neural network models. There's an urban legend about overfitting in the neural network. When neural network model has first been proposed, the scientists used it to detect tanks in the woods. The tanks are usually hidden in the woods. So they want to train a detector. Okay, and the detector has achieved very high accuracy on the test training data, so they are very excited. But after a while, they find that detector does not work on other photos, and they examine the features and the detectors. Finally, they figure out the detector has learned just the illumination of the photos, because all the tanks hidden in the wood are dark. All the photos of tanks in the wood are dark, and all the photos of the tank in the wild are light. So the detector just learned to use the illumination to classify the photos. This is a famous example of overfitting. However, there is no evidence of this story, so it becomes a legend. Prediction error can be decomposed into bias and variance. Okay. So model with high variance it's easy to overfeed to training data and does not generalize very well on unseen test data. This can actually be proved by following formula. Suppose we want to calculate the expectation of the prediction error, square of prediction error. This f hat of x is the prediction, and the capital Y represents the labels. Okay, so after some formulations, you can find that this is actually prediction error is the square of bias plus variance, and the some irreducible error. If you are interested in the proof, you can Google it. So what is bias error and what is variance error? Here are some examples. First, if you have a very good prediction, you have a good model with low bias and low variance, then your predictions will very close to the target. However, if you have high variance but low bias, then your hits will be scattered around the center of the target, right? Because your shooting has high variance, so your hits will be scattered around the target. If you have a high bias but low variance, all your results will be concentrated in a small area, but it's far away from the center. Finally, if you have high bias and high variance, that's terrible. You will be scattered far away from the center. So now we understand that minimize the error is a trade-off between bias and variance. The bias and the variance error depends on the model complexity. If we have a large model which have more complexity, we can reduce the bias in the model error. However, the variance will increase. On the other hand, if we have a lower model complexity, we have a smaller model, then it will have lower variance but higher bias. So the model selection is trying to find the optimal point, the balance between the bias and the variance. So to find the best balance between bias and variance, we need to tune our hyperparameters. For example, the hyperparameters of the regularization is the lambda before the regularization term. Okay, so we can first we need to note that we should never link test data information into our model. So we cannot use test data to tune the hyperparameters. Therefore, we need to split part of our training data and pretend it's as test data. This is called validation data. So we split part of the training data as validation data, and then tune in the hyperparameters on the validation data set. Okay. Now, this approach can make our model better generalized to the future unseen data. Okay. What is the best way to select the validation data set? In fact, we can split our training data set into k partitions and use one of them as validation data in turn. This is called k-fold cross validation. The figure below is a threefold cross validation. Yes. So we split our training data set into 3 partitions and then first select the first one as validation, then tune the parameters, and then we can use the second as validation and tune the parameters, and then the third. And the final score will be the average of the 3 partitions. Okay. In other words, we select the hyperparameter that has highest average accuracy on the 3 cross validation data set. When designing a new model, actually you can select a bigger model first. And since the network has larger capacity, the more capacity the network has, the more quickly it can model the training data, but will susceptible to overfitting. So actually we can let our model overfit first and then gradually constrain it by ending regularization or a new technique called dropout in deep learning. Okay, so how can we spot the overfitting? We need to compare the loss, right? Compare the validation loss and the training loss. Okay. Here is an example of using bigger model. So the original model is the cross shown in the cross. The bigger model will have lower loss. However, it's not stable. And on the validation loss, actually the bigger model has higher validation loss, while the original model has lower validation loss. So to spot overfitting, we need to compare the training loss or training accuracy with the validation loss or validation accuracy. How can we use regularization in Keras? We can import regularizers from Keras and then pass the regularizer into each layer. So actually we can add L1, L2 regularizers in each layer. Here we add 2 L2 node. And from this figure, we can see that after ending the L2 regularization, the bigger model has performed very well, actually performed better than the original model. So when designing new model, we can first let the model overfit data and then gradually add the regularization term or downsize our model. Another common technique in deep learning is dropout. Dropout randomly dropping out, which means sets some output to 0. Drop out a number of output features of the layer during training. Here's the example. It's like a mask out, and set the output to 0. So if the output of this layer is 0, then the following layer won't use the output feature, right? So the purpose is want the next layer focus on the rest of the features and try to make them more robust, train better weight. So dropout can apply to any layer, any output activation at training time, but at test time the activation metric is unchanged. So you can randomly apply dropout to each layer and randomly select some activation function, some output, and set them to 0. By doing this, you want the algorithm to focus on the rest features. So randomly dropout output feature will make your model more robust to unseen data. So let's add dropout to our IMDb movie review classification network. So we randomly drop out 50% of our each layer, of the output of each layer. And then we can find that now the dropout has a bit lower validation loss. Dropout was proposed by Hinton, and this approach is very simple and effective. You can try to combine the dropout with L1 or L2 regularization to see if you can further reduce the validation loss. Finally, let's summarize the machine learning workflow. First, we need to define the problem and assemble a dataset. Then we need to choose a measure of success, such as accuracy, precision, and mean absolute error. And then we need to decide an evaluation protocol, such as squared laws across entropy for different types of algorithms. And then we need to prepare our data, which means we need to do normalization, or sometimes we need to clean outliers or add missing values. And then we need to develop a model that does better than a baseline. So first we need to select a baseline. Our model need to at least compete or better than some traditional algorithms such as KNN. Then we can start to scale up. We first develop a deep learning model that overfits, then gradually regularize our model and tuning hyperparameters by ending L1, L2 norm or dropout to try to reduce the overfitting. And we can also do the cross validation. Those are important steps of machine learning and deep learning workflow. I put this table here again as a reminder of how to use deep learning to solve classification and regression problems. For deep learning, classification and regression are just choosing the right last layer activation and loss function. For binary classification, we use the sigmoid as last layer activation and the binary cross entropy. So this is the same as logistic regression, right? So logistic regression can be viewed as single layer neural network. For multi-class single label classification, we use softmax and the categorical cross entropy. For multi-class multi-label classification, which means we have multiple labels for one feature vector, then we can use sigmoid function and binary cross entropy. This is the same as binary classification. For regression to arbitrary values, we do not have activation function, and we use the mean square error as our loss function. For a regression between 0 and 1 is actually logistic regression, so we use the same activation function as binary classification. But for those function, we can use both the mean square error or binary cross entropy. Let's look at the metrics used to evaluate the performance of our models. Specifically, we want to talk about the accuracy and precision. We will use binary classification as example, but those metrics can be extended to use for multi-class classification. Before we talk about the metrics, we need to understand what confusion matrix is. Here is a table from Wikipedia. Confusion matrix is an important concept in statistics. Suppose we are doing binary classification. There are two kinds of class. One is positive and another one is negative. Depending on your applications, you may want to focus on minimize type 1 error or type 2 error. You can achieve that by adjusting the decision boundary. Based on confusion matrix, we can define a lot of metrics. The most popular metrics, accuracy, is actually the true positive plus the true negative divided by total population. Another popular metric is precision, but precision is only focused on the positive predictions, predicted positive. Right, prediction is only focused on the true positives and the predicted positive. So precision is different from accuracy. One more popular metric is recall. Okay, recall rate. Recall means that how many true positive, how many positive samples do we recall, do we get, right? So it's actually true positive divided by conditional positive. It's also called sensitivity in medical. As you can see, the recall and the precision are focused on different types of predictions. Using both precision and recall, we can observe the trade-off between type 1 error and the type 2 error. So sometimes we will compare the recall with the true negative rate. Recall is also called true positive rate. So sometimes we want to compare true positive rate with true negative rate. True negative rate is also called specificity. So sometimes people say sensitivity versus specificity, or TBR versus TNR. Those are actually the same thing with different terminologies. After learning the confusion matrix, here's an interesting question for you. Here's a news that says 80% of the rapid COVID-19 tests that Czech Republic bought from China are wrong. So it means that the error rate is equal to 80%. This is an extremely high error rate. So many people wonder if the medical staff misused the test kit. If yes, then here comes an important question. Can we just swap the positive class and the negative class and then achieve 80% accuracy? You can think about it using the confusion matrix. This is a very interesting question and is very relevant to our life. The answer is it depends. Depends on what? It depends on how the error rate is calculated. In other words, it actually depends on how the accuracy is calculated. If the error rate is 1 minus accuracy, then yes, we can swap the positive and the negative class. However, we don't have the true condition, right? We don't have the labels of the positive and the negative class of COVID-19. We only keep the conditional positive patients in the hospital. So we highly likely only know the false positive. We only know the type 1 error. So the error rate here is actually 1 minus precision. So the news is saying that the precision is 20%. Because we do not know the true negative samples, we cannot swap the positive class and the negative class because we only know the precisions. Accuracy and the precision means the same thing in English. However, they have different definitions in statistics. Here I list some popular metrics used in machine learning. The notation I use is P for positive samples, N for negative samples, and P prime for predicted positive samples. TP means true positive and TN means true negative. So the recall rate is the true positive divided by the positive samples. And the precision is the true positive divided by the predicted positive samples. The accuracy are the true positive plus the true negative divided by the total samples. And usually we will combine the recall and the precision using a geometric mean. It's called F1 score. Another popular metric is the miss rate, which is 1 minus recall rate. In binary classifiers, we use decision boundary to convert continuous output as binary output, as discrete output. And the choice of decision boundary will affect type 1 and type 2 error. So we need a method to evaluate the quality of a classifier, no matter which decision boundary we choose. So there are two approaches. The first one is called receiver operating characteristic curve, aka ROC curve. This curve draws the true positive rate. It's also called recall, right? The true positive rate versus the false positive rate under different decision boundaries. So suppose we first set the decision boundary equals 1. Which means the probability need to equal or larger than 1 to be classified as positive samples. In this case, no samples will be classified as positive. Maybe only a little fraction. So in this case, the true positive rate and the false positive rate are close to 0. Because the threshold is so high, so all the samples are classified as
negative samples, so there's no conditional true positive. The TPR and the FPR are 0. And in the middle, maybe we will change the threshold. In the middle, maybe the threshold will be like 0.5. And we gradually change the threshold until the threshold approaches 0. When the threshold equals 0, it means that all the samples will be classified as positive. In this case, all the inputs will be classified as positive. So the true positive rate and the false positive rate are both approach to 1. So how can we evaluate the different classifiers? Actually, we prefer the curve that has higher true positive rate when the threshold is very low. If the classifier can have better true positive rate, under lower threshold, it will have larger region. It will have a larger region under the curve. So we will use the AUC, area under the curve, AUC, to compare the performance of different classifiers. The larger the AUC, the better the performance. For the precision recall curve, has a similar function, but slightly different. Right now we use recall. Remember the true positive rate also recall. So recall is very important. So for precision and the recall curve, it's the same story. In this case, we first set the threshold to very high, approach 1. In this case, only the very reliable sample will be classified as positive, so the precision is very high. However, the recall will be almost 0 because only a few samples can be classified as positive sample. Then we gradually change, lower the threshold until the threshold approaches 0. In this case, all the samples are classified as positive, right? So we achieve total recall. We will get all the positive samples. However, there's also a very high false positive rate, which means the precision is very low. Precision is very low. Again, we can use the AUC to compare the performance of different classifiers. So AUC is invariant to the decision of the boundary threshold T. So we can use the receiver operating characteristic ROC curve to evaluate the binary classifier's ability. We need to plot the TPR versus FPR at various thresholds. In other words, with different decision boundaries. And then we can use the area under the curve to evaluate performance. Here's the code to draw this RC curve. Okay, so we randomly create a data set with 1,000 samples. And then we split the data set, use KNN to train the model, and then predict the probability. We need to use the probability to calculate the RC curve. So how can we calculate the probability using KNN? We can use the number of positive samples in the neighbors, right? Then we can call the ROC AUC score to calculate it and plot the curve. We can use a similar code to draw the PR curve, precision recall curve, as well. This time we just call the precision recall curve function and pass the probability as well as the test labels. Test y, then we can use py plot to plot the curve. PR curve is more popular in information retrieval. When should we use RC curve or PR curve? The RC curve should be used when there are roughly equal numbers of observations for each class. In other words, RC should be used when your data set is balanced. The PR curve should be used when the data are imbalanced and we only care about the positive class. In this case, we care more about the precision. So sometimes RC may be harmful because most of the data set in realistic world is imbalanced. For example, object detection. Suppose we want to detect the pedestrians. All the other things in the background are negative samples. So there are a huge number of negative samples. So RC curve can present an overly optimistic view of an algorithm performance if there's a large skew in the class distribution. Here is an example of accuracy and precision from Google Machine Learning Crash Course. You can find this example using the link here. And the task is to classify tumors as malignant or benign. Okay, malignant is bad tumor and benign is good tumor. This is a very common task in medical. Okay, so here is the confusion matrix. We can see they have 9 positive value, 9 malignant, 9 malignant case. The reality is malignant, and for the other negative case, they have 91. So totally, they have 100 samples. In this example, we only classify one of nine malignant samples as true positive. So actually, it's a very bad classifier, right? However, if we use accuracy to calculate the accuracy, then it's a true positive plus true negative. Because there are a lot of negative samples, so no matter what, we still have a very high percentage of true negative rate, right? So finally, the accuracy is 91%, right? 1 plus 90 divided by 100, so it's 91%. It looks very good, but accuracy tells us nothing in imbalanced data. From this example, we can see why accuracy is not good for imbalanced data. We want to focus how good we can classify the positive class, how good we can detect the malignant tumor. Now let's try the precision and recall. For precision, the true positive is 1 and the false positive is 1. So actually the precision is only 0.5. We can see it's low. And then for the recall, we only recall 1 out of 9, right? 1 true positive, but we have 8 false positive. So the recall is 0.11, which is very low. So if we use precision and recall, then we can clearly see how bad our classifier is. And we can try to do some trade-off between precision and recall by adjusting the classification threshold. So if you set the threshold higher, you will have all true positive. Then you will have higher precision but lower recall. If you set a lower threshold, you will have higher recall but lower precision. But still, the performance relies on the classifier itself. So we can use the area under curve to estimate the performance of a classifier. At last, let's review the important concept we have learned about machine learning in today's class. Pedro Domingos, the author of the master algorithm, has written a paper called "A Few Useful Things to Know About Machine Learning," which is a very good paper. So he summarized several useful things to know. The first is generalization that counts. Which means we need to have good performance on test set. Good performance on training set are usually overfitting. Second is data alone is not enough. We need to have prior knowledge about our data. There's a famous theory called no free lunch theory. No matter supervised or unsupervised learning, you need to understand how to evaluate the performance of your model, right? So you need to have some prior knowledge of your data. And then usually we need to label a lot of data. So we need to have expert to label the data. So data alone is not enough. The prior knowledge is very important. The third concept is overfitting has many phases. We know that the prediction error is actually a combination of bias and the variance. So training is minimizing training error is just a trade-off between bias and variance. The next one is intuition fails in high dimensions. Our many algorithms fail in high dimension vector space. So we usually want to reduce the dimension first and then apply the common machine learning algorithms. There's a theory called curse of dimensionality. The higher the dimension, the more difficult to learn a good model. Okay, the fifth one is theoretical guarantees are not what they seem. Usually the theoretical bound for machine learning are very loose, so it's not very useful in real applications. Especially for deep learning, we prefer empirical evidence more than theories. The next is more data beats a clever algorithm. Even sometimes your assumption of the underlying dataset is wrong, but if you have large amount of data, your data are big enough, then usually you will have higher accuracy than the good real algorithm with less data. That's why data is so important. In the AI era, the more data you have, the usually more accurate the model you have. So more data beats a clever algorithm. Finally, learn many models, not just one. So different types of machine learning algorithms are complement to each other. So for industrial application, you can train many different models using different assumptions. For example, combine deep learning with KNN. This can effectively increase the accuracy of your model. In today's class, we have learned many algorithms and machine learning concepts. Here are the key takeaways. First, we have learned classification algorithms. We learned k-nearest neighbor and the linear classification algorithm, perceptron. Also, the large margin algorithm, support vector machine, SVM, and the naive Bayes Also the logistic regression, the sigmoid function, and the cross entropy. And then we introduce the regression algorithm. We have seen linear regression model and how to solve it. And then we know that rigid regression, lasso regression, and elastic net are just linear regression with different regularization terms. And then we talk about how to avoid overfitting by using the regularization and the k-fold cross validation. Finally, we show the example of confusion matrix. We tell you the difference about accuracy and precision recall, and how to use ROC curve to and the precision recall curve (PR curve) area under curve to evaluate the performance of a binary classifier.